Okay, so we're looking at number 8 here. This is our expression for the damped harmonic oscillator. We're talking about underdamping, which means that you basically have like the cosine inside an envelope of decaying exponential, right? So we could write the amplitude as a function of time like this, where a naught, and let me just put this in. A naught is defined to be a at t equals 0. Okay, in case that wasn't clear. So this is what we have, right? The amplitude at some time delta t is going to be given by this expression. And we know, right, we know that this is just going to be the initial amplitude divided by 100 because it decays to 1% of its initial value, right? And so it just comes down to solving this. We have everything that we need, right? This is one equation, one unknown, because you'll probably see that we can cancel the amplitudes, the A naughts. And so it doesn't really matter what A naught is. Does everybody feel okay about like doing the math here? Because you have to do the natural log of both sides after you cancel the A naughts to get rid of the exponential, because we can't have that in there, right? We gotta get rid of it. Is everybody good with that, or do I need to talk about that a little bit? Good. Okay, cool. Oh, touch on it. All right, somebody wants to touch on it. So we'll do that then. Okay, so we cancel the A naughts. And what we end up getting is e to the negative. I'm gonna just so I don't know, just so it's not like I'm doing the whole thing for you. I'll just call this like negative u or something, and it'll also keep the notation a little bit simpler. But after we cancel the A naughts, we get this, right? And if we ln both sides, then what we find is essentially negative u equals ln of 0.01, right? Like this. And then you would just multiply both sides by -1. Then you have u, right? Remember, u is just b times delta t over 2m. And then you can just do the algebra, right? It's just like one equation, one unknown. Is this good? Are people okay with this? Cool. Okay, we'll move on then. Who else wants to suggest a problem? Who else has something? Part 3 of question 6. Let's see what this is. Oh, God help us. This one. Okay. This one. I think this one kind of sucks. But if that's what the people want, I must comply. Okay. I'm gonna talk about the first 2 parts though, because I kind of need to. I haven't looked at this one I think since like last year, so I'm gonna have to kind of make sure that I'm up to speed with everything. Let's see here. Physics lab is demonstrating the principles of simple harmonic motion. Spring affixed to a horizontal support. Okay, after suspending a mass of that from the spring, the student notices the spring is displaced 37.5 centimeters from its previous equilibrium. Spring constant. This is a vertical oscillation, right? Because they say it's affixed to a horizontal support, so I think that means that it's like you could imagine it's like hanging from the ceiling or something, right? I'm gonna just operate under that assumption, and if it's not that way, somebody can correct me. But so if you were to look at the free body diagram for the mass in this case, you would have essentially that. Let me do this. Let me write it out. So we'd want to think about like the net force in the y direction, right? And what we would have is we would have like the spring force is acting up on the mass, and the gravitational force is of course acting down. And if it's, let's see here, if it's come to rest, if it's just like chilling there, then we could set this equal to 0, right? So we see that the spring force has to equal, well, the magnitude of the spring force has to equal the magnitude of the gravitational force. And so the last thing to do here really is just to say that we know the magnitude of the spring force is given by, let's say, K times L, which equals mg. And then here you can see that K is just going to be mg over L. Cool. Is this, I think that's Vanessa. Is this what you did for the first part? Does it look correct? Let's see here. I think so. Okay, cool. So for the next part, this isn't that bad either, right? So don't let the fact that it's like it's vertical mess you up, because the frequency of the oscillation is still going to be the same as the horizontal case, right? So we just recall that this omega is defined to be the square root of K over M. And this should work because what we find actually when we write our differential equation for the vertical case, this is good to see because I think that this could confuse a lot of people, but it's actually not terribly complicated, right? Like, so I'm just going to set up the equation for vertical oscillations and make Mathematica solve the differential equation for me. So it would be like negative k y of t minus mg equals my double dot t of t, right? This is not that different from what we did for the horizontal case. And I'm just telling Mathematica to solve this differential equation for me for y. And we see that, like, so this looks different, right? This is some constant times cosine of omega squared. No, wait, sorry, omega, just omega t, plus some other constant times sine of omega t, but we can always use like trig identities to make this just cosine. And so this would essentially become a cosine of omega t plus phi. And then we just have this factor of minus mg over k to subtract from that. But this is essentially the same thing. The point is that the fact that this is oscillating vertically does not change the frequency. All it does is it changes the equilibrium position. And if you have any questions about this, we can talk more about it. But I just wanted to show everybody that. So this is simply just going to be this, right? What does L represent here? This L? This is the displacement from equilibrium. So for me, it's like the 37.5 centimeters. For you, it's going to be whatever number you have. This should be good for the angular frequency. Now, I don't remember most of these formulas off the top of my head, so I'm going to have to just derive this really quickly. But I do happen to remember that omega equals 2 pi f. And that f, if I'm not mistaken, is 1 over t, which is the period, right? Which is what we want to solve for here. So this is what you got to do for part 2. Okay, let's see about this last part here. I think this is the part that's like obnoxious. Okay, in the final section of the lab, the student is asked to investigate the energy distribution of the spring system described previously. The student pulls the mass down an additional 28.1 centimeters from the equilibrium point of 37.5 centimeters when the mass is stationary, and allows the system to oscillate. Using the equilibrium point of 37.5 centimeters as the 0 point for total potential energy, calculate the velocity and total potential energy for each displacement and insert the correct answer. Okay. So the equilibrium position is the equilibrium position of the spring is also going to be the same, I guess, as our equilibrium position for gravitational potential energy. So if we say something like, for me, I'll call it like this script y. For me, for instance, like y is going to be either 28.1 centimeters or 37.5 centimeters. Then we just do conservation of energy, I guess. However, we will have a negative gravitational potential energy here, right? Because we're taking the equilibrium position of the spring to be at 37.5 centimeters below where it's suspended, and then we pull it down even more, right? So your expression for the gravitational potential energy will be something like negative mgy. And there will correspondingly be an elastic potential energy, right, which would just be 1/2 k y squared. Now we don't need to worry about the sign of this, because remember, elastic potential energy is necessarily positive. And we want to figure out okay, I'm actually a little unclear on this. Like, are we trying to figure out what the velocity is at the equilibrium position? Is that what this is asking? It's kind of what I think. I don't really see what else they could be asking here. Can somebody like confirm though? Is that what they want? While I'm waiting for that, I'll just talk about this really quickly, because like U total is going to be pretty straightforward, right? It should just be UG plus US. So it's negative mgy plus 1/2 ky squared, right? Now, okay, nobody's saying anything. So I'm gonna assume that they want the velocity at the equilibrium position. So what I'll say is, for velocity big V at the equilibrium position, conservation of energy gives, okay, cool. Sanity check there. Just that U, right? Remember, U is the total potential energy. It's the sum of the gravitational potential energy and the elastic potential energy, is going to equal the kinetic energy, right, at the equilibrium position. Now, remember, at the equilibrium position, by definition, we're saying there is no gravitational potential energy or elastic potential energy, right? So we simply write that U is going to equal 1/2 m big V squared, where, remember, big V is the velocity, or we should say the speed, I guess, at the equilibrium position. Even though we'll want to take the positive value here, and the velocity should be pointing up, so I think it's actually fine to call it a velocity. Does this make sense? If there's anybody like trying this in real time, I'd be interested to hear if it's working for you or not before I move on. Because you just got to solve this thing for big V, right? Yeah. Well, we appreciate you nonetheless. Okay. We can always come back to this if need be. Does anybody else have something they want to look at? Any other problems? Who's got some? 5? All right, let's see about 5 here. Oh, I got this one wrong. Yeah. I don't know if I'm gonna be able to do this. Shit. Okay. So I think that one of the things to remember about at least the horizontal simple harmonic motion, and I'll put this in words here, but I'll say like for horizontal simple harmonic motion with no damping, we can write something like this. We can write that the total mechanical energy is always going to be 1/2 k times the amplitude squared. Now, I would assume that he showed you this, but I think that this is something that is not, you know, a bad thing to see multiple times. So like, I'm going to just explain why this is. And it comes from just thinking about the total mechanical energy here, right? Remember, it's oscillating on a horizontal surface, so we don't have to take into account gravitational potential energy. So we're just going to focus on the kinetic and elastic potential energies. So this is what we have, right, for the total energy at any time. Now what we do is we plug in what we have for V from our equations for simple harmonic motion, right? And remember, V is something like -a omega sine omega t plus phi. We have to remember to square this. And then our position for the elastic potential energy term is going to be this expression that we all know and love, right? A cosine omega t plus phi. And we have to square this. Now, like, doing this by hand is kind of gross, but it's okay because, like, I know what's going to happen. It might be a good idea for you to just give it a try. But essentially, because sine squared of something plus cosine squared of that same thing equals 1, this just evaluates to 1/2 k a squared, which is like a really good thing to remember, that the total mechanical energy, regardless of how it's distributed for horizontal simple harmonic motion with no damping, is always equal to 1/2 k times the amplitude of the oscillation squared. So this is what we need here. Okay, so how do we use this, right? Well, if we know what the energy is at any time, I'll say this: the total mechanical energy at any time evaluates to 1/2 k a squared. So we can just do conservation of energy, right? For the we can do conservation of energy to figure out what the speed is of the mass at the equilibrium position, right? So for, let's call this A, conservation of energy gives 1/2 m, and I'll say it's big V again for the equilibrium speed or velocity, and this equals 1/2 k a squared. Right, so if you're wondering what big A is for me, it's this 7.25 centimeters, right? Because if I have some object attached to a spring on a horizontal surface that is at the equilibrium position of the spring, if I pull it back, you know, n meters, if I pull it n meters away from the equilibrium position, it's just going to oscillate with an amplitude of n meters. So you just solve this for V, right? And that's going to give you your max speed. And I think this isn't so bad. You just got to do the algebra and be careful, right? So I'll leave that for you to do. Now B, we'll call this B and C. This is just saying something like V prime equals V over 3, right? Because we're now considering the case where the velocity or the speed is 1/3 the value it was at the equilibrium position. And so conservation of energy is going to give us this. The total mechanical energy. Yeah, you could do that too, actually, for part A. That's also a great way to do this. If you're going to be watching the video later and you obviously can't see what he typed, he said for part A, I found omega, then multiplied it by the amplitude to get the maximum velocity. And that's also a perfectly fine thing to do. So for this part, what we want to do is just write that the kinetic energy plus the elastic potential energy equals 1/2 k a squared, right? I.e. the total energy at any time. And we just fill this in. So we write 1/2 m, then we have big V over 3 squared, not to the 21st, plus, and there will be elastic potential energy here, right? Because we are saying that there is, well, how do I say this? Well, we're saying that the speed is not the maximum speed, and the maximum speed for undamped simple harmonic motion in the horizontal direction always occurs at the equilibrium position. So what we do is we just write this. We have to account for the fact that there's still elastic potential energy because the spring is not at its equilibrium length. And then we just set this equal to 1/2 k a squared. And we just solve for this. We solve for, wait, what do we solve for? We're solving for x. Okay, so we're solving for x. And this actually won't end up being quadratic because, well, okay, let me say it this way. You won't end up having to use like the quadratic formula here or anything because you're going to wind up with an expression where you can just like take the square root of both sides and you're good to go. So you just take what you found for big V up here, plug it in there, easy day. Does this make sense? Is everybody good with this? Okay. Cool. All right. Let's look at, somebody just texted me to look at number 7, so we'll do that. Oh, this godforsaken problem. Okay, yeah. I think I remember how to do this. Let's just take it nice and slow. Okay. So here, the net force on the bolt in the y direction, right, at any time is going to look like this. So just, you know, I'm not going to draw the free body diagram because it's tough when I'm on the computer, but like we would just have the normal force pointing up on the bolt and the gravitational force pointing down, right? So it would look something like this. And from Newton's second law, we can set this equal to ma, right? The y acceleration. But I'm going to be a little more suggestive here, and I'm going to write this as y double dot. And maybe you see where I'm going, and we can actually even say that the normal force is going to depend on time because look, we have an equation here that we think is good. The gravitational force is constant, right? But we'll see that y double dot is a function of time, and that must mean the normal force is a function of time. So when we fill this in, we can write n as a function of t minus mg. Now, this is where we have to remember what the second derivative of a cosine of omega t plus phi is. And so I'm bad at this. Somebody correct me if I'm wrong, but I think that we should get that it's negative a omega squared, and then it should be sine omega t plus phi, right? I mean, this is kind of pathetic, but I can also just check this just to be sure. So we want the second time derivative of it. Oh, it's, wow, okay. I don't think it ends up mattering actually, but it's cosine, so it's good that I checked. Cool, let's just pretend that didn't happen and I know how to do calculus. So I want to just write this one more time for clarity because it'll be better to look at if I just write negative m big A omega squared cosine omega t plus v, like so. Cool. So what we can do is, I guess we can solve this for the normal force. I feel like that's what I want to do, right? So we could say something like the normal force as a function of time is therefore mg minus ma omega squared cosine omega t plus v, right? Just moving the gravitational force to the other side. Now we want maximum amplitude. Or maybe I should solve this for, the right-hand side instead. I think that, yeah, let's try it, whatever, it doesn't hurt to try. So we already have it in the form that we want, essentially. So what we can do is we can write something like this. We can write A equals the normal force as a function of time minus mg, and then we have to divide this by negative omega squared cosine omega t plus phi, like this. Now, let's consider the limiting case where the normal force goes to 0, because that is going to be when the bolt flies off, right? Because if it's not in contact with the piston, then there's obviously no normal force. And so what we find is, I'm just going to copy and paste this because all I have to do is get rid of the normal force, is this. Right, we just pretend that's not there. And the final thing to do here, right, is recall that cosine is bounded. What I mean by this, and I've said this I think a few different times already, but this is a good thing to keep in mind, is that like cosine theta, right, is always greater or equal to -1 and less than or equal to +1, right? And you can convince yourself of this, if you don't believe it, right, you can convince yourself of this just by plotting cosine and looking at the graph, but I think we're probably all good with this. So we could write something like this. We could write cosine of omega t plus phi of the minimum value of it equals -1, right? And so the minimum value of this cosine function is going to correspond to the maximum value of A. So what we would find is that A max equals -mg over, no, this isn't working. Because I want to say that I know the answer works out to be mg over omega squared, but it also doesn't make sense to say that the maximum value of the amplitude corresponds to the maximum value of cosine of omega t plus phi, right? Because A is inversely proportional to the cosine. Hmm. Let me think about this for a second. Okay, I'm not sure I want to fight with this for too long. So let me try this another way. I know we want to think about this. We want to think about the limiting case where the normal force goes to 0. All right, fuck it. I think I'm just gonna leave it at somehow it works out to be that the max amplitude is given by mg over omega squared. I'm not sure what I'm missing here. But somehow the minimum normal force is supposed to correspond to the maximum amplitude of the oscillation, or the geez, how do I say this? Okay, let's just leave it at this. I guess maybe if there's time later, we can come back to this. But this is what you're supposed to do. And I mean, this is good, right? Like up to this point, this is definitely what you're supposed to sort of think about here. I'm just not sure like how. I mean, you could try like taking a time derivative and maximizing, or doing an optimization thing, I should say, like the calculus way, but I feel like that's like a little bit of overkill. It should just work out to be this. I feel a little bad because this is definitely me just like giving you the answer, but you know, sometimes it happens, right? Okay. Are there any other questions? We probably do like one or two more if people have anything they want to ask about. Anybody have anything? Ten. Let's see here. Okay, 2 people want 10. That's cool. Uniform thin rod. Okay, this is going to be a physical pendulum. It looks like. So I need to remind myself what that expression looks like. I could derive it, but I think you've probably seen this derivation done, and it's not super important, I think. So I'm looking at this, right? That you basically find that the period is given by 2 pi times the square root of the moment of inertia of the object, about, or divided by mg times the distance from the axis of rotation to the center of mass. So in this case, the rod is uniform, right? Which means that its center of mass is going to be at its geometric center. So I'll just like put some stuff out here. Let me do this. So for 10, we can say if the rod is L meters long, then its center of mass is at L over 2, right? From the endpoint, we'll say. So it looks like we're going to need the moment of inertia of the rod about a point that is not, or about an axis, let's say, that doesn't pass through its center of mass or one of the endpoints. And so we need to first of all figure out what the moment of inertia is in this case. So we do this with the parallel axis theorem, right? So well, let me just put some words here. We'll say, and if the hole in the rod is at a distance, call it delta L, from the rod's end, then parallel axis theorem, right, tells us this, tells us that the moment of inertia through the axis that we want is given by the moment of inertia of the object about its center of mass plus the mass of the object times the distance between the two axes squared, right? So in this case, it's going to look like this. Now, oh, this is even more annoying than I thought. Okay, because look, we have because delta L is the distance from the rod's endpoint to where the hole is. But we need to actually use the distance from the center of mass to where the hole is, right? And it's not a big deal. I mean, it's not awful, but I do have to adapt this a little bit because I'm gonna make a quick sketch here. Just convince myself that I'm doing this correct because I'd feel bad if I was lying to you. But I think I know what it's supposed to be. And I would suggest that, I'm not going to show you what I'm drawing here, but I would suggest that you convince yourself that this makes sense, what I'm about to write here. So what it's going to end up being is this instead, right? And I think, like I said, I would strongly encourage you to just make a quick sketch and convince yourself that this is what your implementation of the parallel axis theorem ends up looking like. Now, for a uniform rod about its center of mass, if I'm not mistaken, it's like the moment of inertia is 1/12 m L squared. I should probably look this up too. Yeah, okay, cool. I can remember things. So it is going to end up being this. Scribbled, yeah. I don't know about you guys, but I'm so fucking ready for this break. It's gonna be amazing. So this is what your moment of inertia is in this case. And I forgot what did the formula say here? Okay, so we got our moment of inertia about the support, right? That's why they put the support subscript in here, because they want you to remember that it is the moment of inertia about an axis passing through, like, where your given mass is supported, right? And in this case, it's where the rod is nailed to, what is it nailed to? I don't know, the wall, whatever, right? And so you should end up finding though, right, that T is given by, and this is just like an expression that you could find in the textbook or Patrick's probably mentioned. It's just going to be I over mg, and then remember that we want the position of the center of mass here, so we have to use L over 2 instead of just L. Is that correct? It's the distance from the center of mass to the axis of rotation, which I think in this case actually is going to be the same term that we had before. It's going to be this. Is this making sense? I know this is kind of just like me just rambling inanely, but are people understanding what's going on here? Delta L is the length that they give you that isn't the length of the rod. It's going to be, for me, it's like the 0.031 meters. And again, like I would just, well, no, it's just basically delta L is the distance from the end of the rod to where the axis of rotation is, right? To the point where the axis of rotation is passing through. And so I think this is good because it looks like we've successfully used the parallel axis theorem to figure out where or what the new moment of inertia is, right? And then it's just a matter of applying the formula for the physical pendulum, which was this. And again, this would be a good thing to have in your notes or whatever before the exam. Cool. I think this is good. Let's say it's good. Okay. Any last minute questions, I guess, then before we end for the night? I do want to say, as always, you know, if you haven't followed the channel yet, I'd appreciate that. But other than that, I hope everyone has a good break, and you know, feel free to reach out if you need anything from me over the break. Like I said, you know, it's going to be very tempting for a lot of you to, I think, just totally forget about physics for like the next week or whatever, and that's totally understandable. But like, it's not going to help you do well on the exam, and so, you know, just spend a little bit of time thinking about this stuff, and you know, don't come back and just have it all have fallen out of your brain. You should be good. Cool. You know what I want to try? I want to try rating somebody. I've never done this before, so let me see if this works. Oh, wow. It probably would help if I could spell. There we go. There we go. Cool. Okay, watch out. His channel is intended for mature audiences, apparently.